Hello everyone. So in this video, uh, basically we are going to uh, look into a practical approach to solve Bayesian inference. Uh, so Bayesian inference are very infamous, quite infamous for being computationally very expensive. And if we have a large amount of data, then like it becomes so tedious for just to work with the Bayesian inference. Uh, but in this video we are going to explore another approach called variational inference, which is going to reduce the computational time of Bayesian inference. So basically in this complete video, first I will start by what is the Bayesian inference, all the thing about Bayesian inference, and then from the Bayesian inference we will move into their computational challenges and how variational inference is solving that uh, that challenge of the computation. So I have already written a Medium article on this topic, so you can also just go through that article, and I will be using that article as a reference only to explain uh, all the things in this video. So just starting with just giving you a motivation sort of thing that like what is Bayesian inference and all the practical application where Bayesian inference is successfully being used. So it is very widely used concept, by the way, and it is being used in many scientific discoveries. So so just giving you a motivating example so that you can jump into explore more into this topic, and this is very interesting topic as well. So some of the few examples of Bayesian inference is, first is it is being used in discovery of a exoplanet, which is a uh, TRAPPIST one. So in this exoplanet discovery, basically Bayesian inference is being used to give a estimate of a candidate object. So we have a like lot of a candidate objects that can potentially be your planet, right? So Bayesian inference is being used to provide the estimate that how much probability of a candidate object has to become a planet. So this is how the how Bayesian inference has been used. Another important discovery of a gravitational wave, where Bayesian inference has been successfully used. So Bayesian inference discovery is one of the major discovery in physics, and it proved the Einstein theory of relativity and how gravitational work in space and time. So Bayesian inference has been successfully utilized basically in the discovery of gravitational wave. And if you want to learn more about this, you can follow this article. uh, Another important applications where Bayesian inference is being used is to give a estimate of travel time of a vehicle between two location, which is basically in a problem of routing, and many big companies like Uber is using this thing in its platform. So basically it what Bayesian inference is doing, that it is providing with a better estimate of your predictions in the travel time. So, and it is very important, by the way, because let's say if you are driving an ambulance and you have a just 12 minutes to save a patient, and you have a two route to choose, and one route is saying that okay, it on average it will take 9 minutes, but it has a plus minus 5 minute of uncertainty, while another route will take 10 minutes but it has plus minus 1 minute of uncertainty. So and you have a 12 minute to save that patience. So which route you will choose? So basically, obviously you will choose the another route because it is more certain. Like you have, although the mean time that is it is taking is a 10, but on average time it is taking a 10, but it has like more certain around that time, right? Rather than choosing this 9 minute, because in worst case you can end up losing that patient. So you don't want that, right? So and this is very risky situation, and in most of the risky situations you need to have that estimate that okay, you need to have that confidence interval. So and Bayesian inference is basically utilized to gain a better understanding of as uncertainty associated with the each prediction. And so we discussed some of the applications of a Bayesian inference, but let's understand what exactly is the Bayesian inference. Okay, so suppose we so that as we have given an example, suppose we are solving a problem to predict the time taken for the bus to travel between two places. So in this case, our unknown is what? Time travel, right? So let's say time travel depend upon some parameter, and it can be like time travel, it can depend upon, let's say, traffic. Theta 1 is the theta 1 into traffic, then plus theta 2 into you can say driving behavior or something, plus theta 3, something like that, you know. So we have a two or three parameters here, like theta 1, theta 2, theta 3. It can be like theta n also. So let's say we have this parameter, and these parameters are unknown for us because we don't know that how much our travel time is dependent upon traffic, or how much our travel time is dependent upon the how the driver is driving the car, and another factor. So these all factors are unknown for us, right? So we define that unknown unknown parameters by some theta, right? And let's say for simplicity it is only depending upon one parameter, let's say traffic, and you don't know the you don't know the theta 1 of traffic. So you have defined your parameter theta. Now we have some prior knowledge for our parameter. We have to know some prior, so in the Bayesian setting, what we'll do that, let's say we have a theta 1 which is very unknown for us, but we defined a prior for our theta, and that prior will give you prior will come from your the understanding of the understanding of the you can say the domain, that how much what should be your prior. So prior basically give you a somewhat estimate without knowing a theta, what is the best you can say about that, what is the best distribution that you can say about that theta. In this case theta can be anything. Let's imagine that you have defined your prior as a Poisson of 5. Just to give you defining a prior and choosing a prior is itself a very important topic, and it require a lot of exploration and lot of study, a lot of deep dive into it, and it is very well explored topic as well, so you can always find a lot of resources around it, so you can always go ahead and check it. So we have a how to drive, how to come up with a good prior, and coming up with good prior is very important also, because it all the further exploration depend upon that. After defining prior, we have to define the likelihood as the probability of observed value given parameter. So what I meant by is that uh, we will have some data set, right? X1 to xn as a data set, which is like in this case it can be all the all the travel time of the buses or some vehicle, right? So it can be like 2 minutes, 3 minutes, 4 minutes, like that. Okay. So given these all data set, these are the data set that we have. So what is the likelihood of that data given this theta? So you define a likelihood, what is the more you can say that suppose we have this theta about we have this prior about uh, we have this prior about theta, and given this prior of theta, or given this theta, what is the likelihood that we will get this data x1, x2, xn. So this is how we are defining our you can say likelihood. So likelihood is defined as a likelihood of getting that data that we have right now, considering we are working with this particular theta. And likelihood which also come from the our knowledge about domain, or you can just check that how this distribution is how this data is following closely to which distribution. So more of this likelihood and prior come from our understanding of the knowledge as well as looking into data. So this both thing, given this both prior and likelihood, we have to now we have to find our like we have to update the knowledge about our theta. So what I meant by is that, okay, let's say we have the knowledge about our prior, we have some knowledge about our prior, our theta, some knowledge about our theta, which we are calling as a prior, and now we have observed the data. Then how our knowledge about that theta is changing, right? We have to calculate the posterior, which we call as a posterior. So considering that we have some knowledge about when we have a no knowledge about theta, then theta was like something like let's say normal of 0 and sigma 1, right? And and we had some likelihood, right? Like probability of data x1 xn given some theta should be like normal of again 0 or sigma 2. Now we have some knowledge because we have observed the data, like we have the data. Then how the knowledge of like what is the probability of theta given that we have observed the data, how it changed. So this part we call as a posterior. So how to define the posterior? So posterior, so you can, this is a pictorial representation and this is a very good representation. Let's see, we have some prior about the theta. This is the prior distribution of theta. This is the prior distribution of the parameter, and our we have like more very uncertain about, like it can be equally like it can have a equal value at this point, at this point, both are equally likely to have, right? This and this is equally likely to have. This is also somewhat like variance is very high in this case. But in this case, once we have observed the data, our prior, like our posterior of the theta get changed, and it become like now what you can say that we have a high chance of having theta as this thing, right? And this is like a very low chance of having this theta, right? So now our variance become very variance get reduced, and we have now better knowledge about the theta because we have observed our data. So we now have a better knowledge. So before we had a very vague knowledge about our theta, but now we have a better knowledge about our theta. So we can confidently say something something about that theta. So how to define that posterior? Posterior is given by what? Probability of theta given that data set. So our posterior is defined by this formula. So this is the posterior, like this is this is nothing but likelihood, and this is prior, and this is the normalization constant. Where so this is the Bayes theorem basically. This is this formula come from the Bayes theorem. So when we are using Bayes theorem, the probability of a theta given the data, this we get this. Okay, so now let's look. Looks good till now that we will have to update this. Update our belief about it, and we are now good to go. That okay, our variance will reduce, and we will get a good estimate about the parameters. But now the computational challenges things come into the picture, because of this integration term. This integration term is not very and like easy analytically to calculate. Sometimes it's impossible analytically to calculate. So we have to like we have to estimate this integration using some methods. So we have some methods we have lot of methods being used to calculate the integration of denominator like this term. But we have like something called MCMC, which is widely used and which is very accurate, but the challenge is it's very computationally expensive. So sometimes it is so expensive that it can even take like 1 or 2 days to come up with some solution. So MCMC is a good approach, and many people have been using it, but they are computationally expensive. But which is the thing is this is accurate. So just to reduce the computational time, we have another approach that is called variational inference. So which proved to work, and it's computationally very faster compared to MCMC. It's like variational inferences will take like 10 or not even a 10 minute I think to perform some inference. And so in this this article, basically this video, we are mostly going to talk about this mostly going to understand the variational inference, the concept of variational inference. So let's redefine our goal basically. So our goal is to compute this value, right? Compute the posterior basically, which is not easy to compute analytically because of this integration term. Okay, so so what we are going to do, we are going to, like, we have a distribution that like this posterior is nothing but a probability distribution, right? This will be a probability distribution. So what we are going to do, we are just going to uh, estimate this probability distribution by some another probability distribution. What I meant by is that that, like, let's say we have this posterior, right? uh, and this is the posterior distribution. So we will just say that, okay, I wanted to it it should be I wanted to approximate this distribution with another distribution called q theta. We have a p theta already, and we want to approximate this distribution by some distribution q theta, and that q theta is something, it's some distribution we already have much information about. It could be some standard like normal with some mu and sigma, and mu sigma can be complicated, like, it can be anything. Okay, so so thing is, like, let's say we have this distribution, but rather than having this distribution, we wanted that, okay, and this is very computational, like you cannot do any inference with that. So you wanted to have a distribution something like this, which is close to this. I'm just giving you an example. Okay, so this is something, and we are saying this as a q theta. Okay, so and so now we so it's not like it's exactly going to be this, so obviously it's not a perfect solution. It is just a it just a s- it just it's a approximate solution of variational inference is going to give you approximate solution of this posterior. Okay, and this trick, like this simple trick, means that we don't need to worry about this integration, and this is which is very important for us, because this integration is something which is not trivial to solve. So yeah, so now the question is how to approximate that q theta. Okay, so now the bigger question is, okay, we are saying that we are going to approximate this posterior with some q theta. So now how to find that q theta? What will be that q theta? So first information that we have about q theta is that it should be some, you know it should be some following some standard distribution, like normal or something, normal exponential, something like that, right? So we have a whole inverse of distribution from which we need to find our approximate q theta distribution, right? And from this whole inverse set of distribution, we are only interested in some nice set of distribution. So what do you mean by nice set of distribution? First thing is that, okay, so nice distribution means that it should be, so what do you mean by nice set of distribution? Remember, we have to report the mean and variance of our distribution, right? Because if we are talking about a nice set of distribution, like so it usually means like some standard distribution from uh, which means and variance you can easily compute, because at the end what we wanted to get the mean and variance of this theta, right? So if we will have some distribution from which mean and variance is easy to compute, it is good for us, right? So we wanted to report mean and variance of distribution, so we are interested in distribution which mean and variance are easy to compute. So this is our basically definition of nice set of distribution. So from a universal set of, here I am giving you a idea about picture. So this is the universal set of, this is the set of distribution, this is the whole inverse of distribution, right? And this is your p theta here, and in this whole set of distribution, this is your p theta. And this here is inside this whole set of distribution, you have some nice distribution. Okay, this is the nice distribution, and you have to find a q theta somewhere here which is closest to p theta. Okay, it's better if you will find here, like it I'm just giving you an example, like this could be closest to the, your q theta should be closest to the posterior from this nice set of distribution. So this is our goal now. Okay, so just expressing above this thing into like a equation, it become like, you have to find a q star which will minimize the distance between some sort of distance. We will talk about what that distance means. but some sort of distance between q theta and your posterior. Yeah, and here this f represent the distance between two distribution, like this distribution and this distribution. So what that distance mean? So distance means just like, how closest your distribution is. Okay, so in this case we are using the KL divergence as a metric to calculate the distance between two distribution. Okay, we can use another metric always also, but KL divergence is a faster. So now uh, what we say, we need to calculate the q with the minimum KL divergence between between q theta and p theta. Okay, so we need to calculate the q. So now our goal is to just calculate the q which has a minimum KL divergence between your posterior and q theta. So this is now our problem statement. This is now our goal is. So what is the KL divergence of this two distribution is given by KL divergence is given by this this q theta into log p theta. If we are taking the KL divergence between q theta and your posterior, which is p theta given x, then it is given by q theta into log of q theta y में uh, p theta given x into d theta. Okay, these are the like the formula for KL divergence. Okay, but for calculating KL divergence, okay, so one another loophole came here. So just to calculate this KL divergence, you need to know this posterior, right? And this is exactly what we don't know. Okay, so now how we are going to do that? Like, this is exactly what we are computing, and now we are saying that okay, calculate the KL divergence between two distribution, and we don't know about anything about the about the posterior. This is what our goal is to calculate. So we are sort of in a loop, right? Okay, to calculate this we need to know this. So there is no point. So are we hopeless? We are not so hopeless. Let's do some algebraic manipulation. So what we just we just multiply and divided this thing by uh, px, which is a distribution. Okay, so after multiplying and dividing this, like if you look at it like denominator, this will become p theta given x. This come from the base like theorem, like just p theta given x into px is equal to joint distribution of theta and x. So now let's do some let's do some math around it, and just by doing like just doing some log manipulation, because this thing is minus, so it will become log px and minus then yeah, q theta x and then q theta d theta. How it come? Because we have taken minus here, and then minus sign will this q theta will be on outside, and then like that. Okay, so this is how we are taking. Now look at this equation. So just by doing some manipulation, you will understand that how we come from this here to here. Just look at this equation. Okay, so in this case you can take log px outside, right? You can take log px outside, and then this become because this is independent of theta, so you can take log px outside, and then this becomes just a q theta d theta, and just know that q theta is your probability distribution. So if this is a probability distribution, q theta d theta will become what? 1, right? Because this is the property of the probability distribution, right? Integrating over all the possible theta will get you 1, so this will become 1. So now this above equation can be written as like log px minus uh, q theta into log p theta upon my q theta d theta. Okay, okay, we come till here. So now our goal is to minimize above term. So just don't forget our goal. What is our goal is? Our goal is to minimize above term, this term, because this is the KL divergence, right? So we have to minimize this KL divergence distance. So we have to minimize the above term with respect to q theta. We need to find a q theta that will minimize this term. So just to understand this, minimizing these terms, because this is a constant, right? So minimizing this term is equal to maximizing this term, isn't it? So because this is a constant, so either we will minimize this whole term, or it doesn't affect anyway, so we just need to maximize this term because we have a minus sign here. So is equivalent to maximize this sign. This is what we called as a lower evidence lower bound. And this above term is called as a low elbow, lower evidence bound. Why we call this as elbow? Because we have some bond about that uh, this is bounded by, like, this above term is bounded by this log px is bounded by this term. So so that's why we call them as a elbow. So now our target become max find a q which can maximizing our elbow, right? So our target now is to maximize this elbow term, right? Now let's look back into the constraint of q theta. Okay, so now let's go back to constraint of q theta. So now our target is just to maximize this term, and our constraint is that we need to find q theta from the nice distribution, right? Because we need some distribution that can that from where we can calculate mean and variance easily, right? So let's take some more time to define what is the nice distribution. We have talked about little bit about that also, but let's define it more concretely. So distribution which can let you find mean and variance easily. So what can be the possible case of this distribution? So obtain exponential family is a good candidate. All the exponential family that your exponential family of distribution is very good candidate because it can let you find mean and variance very easily. Then another thing is that you need to have a low dimension distribution, right? If it is a low dimension distribution, then calculating mean and variance will be very easy, right? So which lead to your MFVP mean field variant Bayes theory. It's a class of distribution basically which follow this rule, you can say this constraint. So when we are saying that MVP class of distribution, this means that it follow this constraint, and that is that let's say you have a let's say you have a 10 dimensional theta 1 theta 2 theta 3, and you have some distribution around it which is given by q theta. So you can write this as a q theta 1 into q theta 2 q1 q2 into q3 theta 3. So this can let you do that. This class of distribution follow this thing. So now you have a higher dimensional, higher, you have a distribution in a higher dimension, and now you have break that distribution of higher dimension into lower dimension. This is the concept of MFVP basically, mean field variance page. So what it let you do, it is let you break down the higher dimensional into the smaller distribution, and this class of distribution is very useful when in computing the variational inference. So okay, now we get into two things, that two property which can make a distribution nice distribution. First thing is that easy to compute mean and variance, that is exponential family is a good thing to do. Another thing is that low dimensional distribution, which means that MFVP class of distribution, which can let you break down the higher dimensional distribution into a smaller distribution. If we have a like higher dimensional unknown theta 1 theta 2 till theta n, then we can simply break down into theta 1 into theta n, and it will be very easier to calculate because like we only need to worry about individual component, right? So okay, now we come till this point that okay, I have to calculate q star which maximize the elbow, which using the MFVP class of distribution. So we have to like we come till this point. Okay, okay, so now for calculating q star, which use q star which maximize the elbow, you need a calculus of variations. And by using calculus of variation, you can show that the q star which maximize elbow is given by this thing. But I don't want to go into mathematical detail of how how this came, how this drive. If you want to go detail into that, you can always look into literatures. But yeah, just for purpose of keeping mathematical jargon outside from this outside a scope of this video, I just wanted to just give you a concrete overview that okay, this by using calculus of variation you can come up with this solution. Just look at this thing above. By equation can be written as, just manipulating it, this can be written as this, right? I know Ellen, just taking log both side, right? Yeah, and just see like this term is a constant, so we don't need to worry much about this constant. This term is constant, so yes, we just need to, yeah, this above term can be written in this, right? Okay. Now what? Now after solving the above equation, we will get the standard distribution like exponential or q star. Okay, this is also a well defined, like you will be given some distribution of p theta given x, and just put that distribution, you will get a standard distribution. Uh, this is also a advantage of using MFVP class of distribution. So you will get a standard distribution for q star. Now how to solve the above equation to get the distribution of q star? So above equation can be solved by EM algorithm. So and just understand it. So let's say we have a two parameters theta 1 and theta 2. Okay, just look at this equation and you will find, let's see, our theta 1, like this, in this case when we are saying the j, right, j theta 1 q star 1 theta 1 j given x, it is just only dependent upon minus j, means like another parameter which is not theta 1, which is not 1, like it can be 2 3, right? So our theta 1 in this case, if we have a two dimension, like two elements in the parameter, then our first parameter theta 1 will only depend upon theta 2. It doesn't have a theta 1 term here, right? Theta 1 term is nowhere, so it will be the expectation over the theta 1. So just writing this here, that q1 theta 1 distribution will be some standard distribution. It can be normal, Gaussian or something like that. It can be normal, some exponential family of distribution, and it, which parameter will be dependent upon distribution of a q star 2. इसका, the parameter of this one, like that standard distribution will dependent upon only on the q star q2. It will not depend upon the q1. Okay, similarly for q2 star 2, it will only depend upon the q1, not on q2. Now what we are doing, we have created a circular dependency where distribution of q star depend upon the distribution of q star 2. Now we are using the EM algorithm. So EM algorithm, what is EM algorithm does? So just to giving overview. First we are initializing some random parameter for of q1. So we are just taking the q1 ka, just initialize some random parameter of the q1. Okay, when we initialize some random parameter of a q1, let's say it is normal, 0 2 or something, like, okay, then since for calculating q2 you only need q1, right? So what we do, we can always calculate q2 now. Just calculate q2. Again you will get something, some distribution of q2. From the q2 again calculate q1. Now your q1 will get updated, right? Again from q1 you have to calculate q2, and repeat this until you have seen no change in parameter of a q1, q star and q star and q2 star. Okay, just to explain you once more. So what we are doing, we are creating a circular dependency of q1 into q2 and q2 on q1. So now we have initialized some parameter of a q1, like let's say if it is following a normal mu sigma, then we have initialized some mu and sigma for q1, that is that is like let's say 0 and 2. And now what we are doing, uh, be, because our q2 is only dependent upon the q1, so we can always calculate q2 from the q1. So we will have some, let's say 1 and 5 will be the parameter distribution for q2. Now what we are saying, because now our q2, we know that q2 is dependent upon q1, so we are again calculating q1, and let's say our q1 initially initialized was 0 2, but it will get to 0.5 or 3, something like that. Now from the q3 again calculate q2 and do it until, like, when you can see the negligible change in the parameter. So repeat this process until you change the negligible parameter in q1 star 2, q1 star 2 and q2 star 2. And this is how you will calculate the all the parameter of q1 star and q2 star 2, which is like, q1 star theta 1 and q2 star theta 2, which will help you, to get a distribution of a theta 1 theta 2. And which distribution, this is the q1, because it is equal to q1 theta 1 into q2 theta 2 by using MFVP, right? So now this q distribution that we are taking, this is the same distribution that is maximizing the elbow, and this is the same distribution that is closest from your posterior. So now this is how you calculate your posterior, and this is how variational inferences work. It's computing your posterior. Okay. So now let's understand when variational inference will not work better. So we have made some assumption that all the unknown parameter will be independent of each other. Like when we are using the MVP class of distribution, then we have assumed that all the distribution theta 1, theta 2 are independent of each other, right? But when our parameter will dependent upon each other, so it will not it will not work well. So this is the only assumption about variational inference, that just check that either your parameters are independent or not. So hope you like this video. If you have liked this video, please don't forget to like and subscribe.